Now we'll discuss how we can specify the semantics of a programming language. So what do I mean by programming language semantics? For every language expression or statement, what is its meaning? So for example, when I say x equals 0, what is it supposed to do to the state of the program? Now this is where a equals here is supposed to be, let's say, the assignment operator. Now we already informally understand what it's supposed to do. In fact, these are the semantics that we informally assumed when we did code generation, for example. But we want to make it more formal. And so in general, if I look at a programming language, it has many definitions. For example, it has the definition of tokens, which is, for example, specified using regular expressions. And that's useful for lexical analysis. You have the specification of a grammar, which is used for syntactic analysis. You have a specification of typing rules, which is used for semantic analysis. And then next we are going to discuss the specification of evaluation rules, which is the actual meaning of the program execution. And this is important for code generation and optimization. So far, our code generation strategy has informally assumed the semantics, but we should formalize it so that we can be sure that what we are doing is as per the intended semantics of the language when we are doing code generation. All right. So, for example, during code generation for a stack machine, we have informally assumed the semantics of a language. For example, we have informally assumed the meaning of a function declaration or the meaning of an operator plus and things like that. Why do I say it was informal? For example, we never say whether plus is supposed to be meant for, what is it meant for? Is it meant for integers or whether it's meant for floating point? How big is an integer? How big can an integer be? Is it in mathematical integer, which means can it be infinite size? Of course not. So what is the limit of size that it can have? All these things we have kind of omitted in our informal description of what the program is supposed to do. And we even generated code for using that informal description without actually specifying these things. For example, when we generate the code for addition, we didn't even specify what's the maximum size that an integer can be. We just assumed that whatever the register can hold is good enough, and that was a 32-bit value in the case of the MIPS architecture that we were generating code for. But does that agree with what the language designer expected the language to do? So these are all things that need to be formalized and specified to the exact with the exact precision, so that we can be sure that the code that we're generating is actually matching the language designer's expectations. So we want to formalize this informal specification. And one way to do that is to specify the formal semantics of a stack machine. So here's one proposal, which is not a good proposal, that we just have a stack machine and we know what a stack machine is going to do. We have the notion of registers is a 32-bit. We have the semantics of all the opcodes like add, IU, and pop and push and all that. And then we just specify the code generator function cgen and say, if you see this operator, then this is the code that you should generate. And because in that code we have 3 or 4 instructions, and for each instruction we know the semantics. So from that we know the semantics of every operator. And that would be one way of specifying the formal semantics of a programming language. So once again, what is the proposal? You first specify the formal semantics of the low-level assembly language. Then you specify the cgen function that's going to translate to that assembly language, and there you are. You have the semantics of the high-level language because you have the cgen function and you have the semantics of the lower-level language. But that's not satisfactory because it would be correct, but it would be too restrictive. Because there are many choices that you make during cgen, and if you kind of just say that these are the choices that must be followed all the time, then it's too restrictive. For example, if I generate code for another machine which has larger number of opcodes, it gives me potential to do things differently. I won't be able to do it because with these semantics, I'm constrained to, for example, use the same meaning. For example, so what do I mean by correct but too restrictive? It's an over specification. So we are over specifying in this way of specifying the semantics because we are specifying that we should only use 3 or 4 registers. We should only grow the stack downwards and so on and so forth. And these things were not really meant to be specified in the original language. And that's why it's an overspecification. So assembly language descriptions of programming language implementations will have irrelevant detail, like whether to use a stack machine at all or not, whether the stack grows upward or downward, what is the number of registers, what is the representation of an integer. For example, is it a 2's complement representation, or is it something else, maybe 1's complement, or something totally different. What is the instruction set that I am allowed to use. So all these things I don't want to specify when I'm designing a programming language. For example, a programming language like C or C++. And so I should have a more higher level way of specifying the semantics of a programming language that allows me the flexibility to choose these implementation level details for a given architecture, machine architecture. So we need a complete description that is not overly restrictive. And we need a high level way of describing the behavior of a language. Now, one approach to doing this is to have a reference implementation. For example, I could have a program emulator, right? So you give it a program and it's going to generate the result, and then you can say, whatever result this program generates, that's the program, that's the same result that your code generation strategy should also emit. And that would be one way of specifying the semantics. But that's also not satisfactory, because again, there will be artifacts of the way this reference implementation was implemented. Once again, how big was an integer? What is the, how are things implemented? All those artifacts would become part of the language, because I'll have to kind of obey that those artifacts. How is the output represented, for example, and so on. And once again, that would be an over specification. And so that would not be an acceptable approach. We are looking for semantics which need not be necessarily executable, but they need not be executable, but they should give you as much generality as possible in your space of implementations. And that would be a precise specification rather than an over specification. So we need an abstract method of specifying the meaning of a program precisely. It should be mathematically precise in the sense that it should be correct. That's requirement one. Both the proposals that I have discussed so far are correct. Whether I generate assembly language or you use a reference implementation, they're both correct, but they're not general in the sense that they kind of thwart many behaviors that were possible. They just kind of disallow that kind of thing. So we want it to be as general as possible while being correct, right? So for example, I could have an abstract machine. So I could basically imagine that there is some machine which has the notion of an integer, and then there is this plus, then I can say what is the size of an integer. But these are all abstract things. They need not be executable, it need not be physically realizable, but there is the notion of some abstraction, and as long as we are true to this abstraction, that can basically serve as a specification, and then an implementation should basically adhere to this abstract specification.